What's up? What's up? It is Tuesday, September 10th. Yeah, maybe I should look at the actual camera. All right, there we go. Never back down, never what? Never give up. Okay, cool. So hopefully you got everything in there. Let's rock and roll. Okay, cool. So we have the journal check number 3. It is coming up this Friday. So make sure that you're ready. I did already what did we do? Oh, I don't know why I put entry activities 4 through 5. Anyway, we'll get that fixed. But I think it's gonna be 5 through 6. That's my bad. Matter of fact, we could probably fix it like right. Bam! As you can see, it is fixed now. So 5 through 6. Motion, weight, mass, interacting objects, forces, speed formula. You see all these things. So we got quite a bit of things to do. We've taken the notes for motion. We already wrote down the speed formula as well. So we'll just keep going in that direction. So, cool. Now, this is kind of where we ended off yesterday, and we were doing some calculating, and we got some things taken care of there, right? So we used the speed formula. Speed is equal to distance divided by time. By the way, you are going to need to memorize that, okay? And this formula is not too crazy. Again, it's speed, so S is equal to D divided by T, and this line right here is the division line. So again, we did the 100 meters divided by 9.79 seconds, and then we got 10.2 meters per second. That's how fast they were traveling. Some important things to, let's go back. Some important things to make sure that you notate is that we did not lose the units. Now, if you look over here, speed does not have a specific unit. Some formulas do. We'll put those in the formula. This one does not. So it could have been miles per, right, or miles over hours, right? You could have done that. You could do miles per minute. You could do any of those things. So as long as you have a distance on top, it's not specified, and you have a time on the bottom, whatever time increment you would like to use, then you can calculate the speed of an object. And remember, we said it was the average speed, not the total, not the maximum speed, but the average speed of that entire 100 meters. Okay, cool. So we talked about this as well yesterday, so I just want to make sure we're good, that you guys see, like, hey, this is where we're at right here. This is the ones place. This will be the tens digit, right? But once we go to the right of the decimal place, then we're at the tenths, hundreds, thousandths, right? And then I also want to clarify just this miles per hour. So this is the miles. The per is the line, the division line over 1 hour. So make sure when you see it like this, right, you guys think of a fraction, but remember, it really is division. It's division that is right there, okay? Cool. Let's keep it moving. All right. Oh my gosh. I don't know if y'all saw that. So can you tell us the definition of motion? Hopefully you said the change in an object's what? Position, location with respect to time in comparison to the position of other objects used as reference points. If you gave me at least that first part, the change in an object's position or location in a certain amount of time, then you're doing good. The reference points, we'll talk a little bit more about that later. Okay, cool. Now let's move to this. So what we're gonna do now is, you guys do have the speed formula, so you already got that. Can you calculate the speed of the person who came in? Let's just pick, I actually follow this person on Instagram, so let's pick Kung Fu Kenny. You guys are like, what? Yeah, right here, Kung Fu Kenny Bernadette. So his time was 9.88. Let's just see if his is any different. So again, the distance, we have that clocked in because we have the men's 100 meters, right? Right there, so 100 meters, boom. And then we're going to go and say, okay, what was the time? The time was 9.88 seconds. And then we're just going to go equal to, and then let's go ahead and get my handy dandy calculator out. Bam. Let's go ahead and get that. Okay, and then we're just going to go 100 divided by 9.88. Bam. So, and if you take a look, and again, we're going to round to 1 decimal place. He was running at 10.1 meters per second on average. That is how close. We're talking about a tenth of a meter, right? A tenth of a meter. That's all we're talking about. A tenth of a meter. It's a super small amount. As a matter of fact, I'm gonna pause it so I can get the meter stick. I'm gonna show you guys. Okay, so on a meter stick, you guys may not be able to see everything, so we're gonna zoom in just a little bit. Right there, there's 0, and it goes all the way to 100, and these are all what we would call centimeters. So that word centa is like century, cents, that's like 100. So that means that every second that they were running, Kung Fu Kenny Bernadette, was falling behind by this much for every second. So a tenth of a meter. So in the first second, he was behind by that much. Second, third second. So he's falling behind on that much. So if you say like, oh, well, over 10 seconds, then that means he was behind Noah Lyles, right, on average average speed by about 1 meter. And that's why this race was like really close. You see, like everybody was like right on top of each other. So it's not really that big of a distance. But because his speed was just a little bit less over, you see, a length of time, then that actually begins to make a difference. And you kind of see how that starts to add up. Okay, cool. Let's keep it pushing, and we're going to turn that off and then keep going. All right, so let's just talk about the metric system for just a little bit here. First, I would want to know, what do you know about the metric system? What is it that you know? Do you know anything about the metric system at all? A lot of students do not. Now, we were just literally using the metric system. Most people may or may not know that meters, centimeters are all inside of the metric system. So we're going to take a little bit of a look at that today. So first things first, though, before we get into the metric system and start talking deeper about that, let's talk about the difference between weight and mass, okay? So, and write this down in your journal. So weight is how much gravity pulls on that stuff. Mass is how much stuff something is made of. So the stuff that's inside, right? So the stuff that's inside. And again, gravity, right? Weight is a measure of how gravity pulls down on that stuff, okay? So get this notated, and then we're going to look at an example I'm going to show you. Okay, so remember, mass is how much stuff something is made out of. So, cool, let's just talk about that for a second. Boom. So, if you look, I actually have 2 boxes here. I have 2 boxes. One box looks like that. And then I have another box that looks like this. These boxes are about the same. Let me move the microphone just a little bit. These boxes are about the same as you guys can see in height, height, length, and in width. These boxes are approximately the same. So we would say they take up the same volume, or they take up the same amount of space. Now, mass is a measure of how much stuff something is made out of. Now, here's the thing. These 2 boxes are very different as far as their mass. And the reason is because, peep this out. This box, bam, there's nothing in there. So it's not made of very much stuff, right? So it's not made of very much stuff. Now, this box, on the other hand, is made of quite a bit more stuff. And for me to try and throw it, right, as you can see. And as you could see, when it hit, you saw some vibrations and stuff. That's because gravity was able to pull down more on this box because it had a bigger mass. Remember, weight is a measure of how gravity is able to pull down on the mass of a box. Again, watch, see, look. Okay, now watch this one. Watch this one. Watch that shape. Oh, a lot more force is coming down because gravity has a lot more mass, right, to pull down on. And that is the difference between weight and mass. And just remember, just because the volume or the space an object takes up is the same, does not mean that they have the same weight or mass, okay? It just means they take up the same amount of space. Cool, I just wanted to get that. All right, now that we've got that cleared up, let's move on to some things here. So, your mass remains the same, right? Well, your mass will remain the same. So the stuff that you're made of will remain the same. So if I took both those boxes to the moon, they would remain the same. The stuff that's inside will remain the same. However, if gravity changes, since weight is beholden to gravity, then if the gravity changes, then your weight will change, not the stuff. So if I went, because I weigh about 200 pounds, and if I went from Earth to the moon, my weight would change. But the mass, the stuff that I am made out of would not. I am still the same, okay? So cool. So if you just take a look at this, I do want to point this out. We usually like to use pounds in what we would call the U.S. customary units. Those are like pounds, or what you guys know as feet, inches. Those are the U.S. customary units. But just know that the rest of the world and science, we use the metric system. So instead of pounds, what we use is newtons. So now we're back to newtons. So if you look, right, the mass of 45.4 kilograms, and kilograms is what for the metric system is what we use instead of pounds, right? Then, I mean, it's for mass, right? That's what we're going to use for the measurement for mass. It would be the 45.4 kilograms, right? But when you actually do some math, and we'll talk about how did we get to these numbers. We'll talk about that a little bit, because it's, and how you measure, how you are able to find weight. We'll talk about that. So your weight, as you can see, on each one of these planets is different, because the gravity on each one of these planets is different. So the gravitational constant for Earth is 9.8 meters per second squared. You guys will memorize that by the end of the year, don't worry. The gravitational constant for the moon is 1.62 meters per second squared. And you can tell that it's so much lower, as you can tell that, yes, oh my gosh, the weight is so much lower. So is the gravity on Mars higher than the moon or lower than the moon? Hopefully you said higher, because the weight is higher. That's correct. So, and you could tell, like, oh, this number is a little bit more than double. So you can see the gravity is a little bit more than double. It's very proportional. So what would you guess would, just based off these gravities here and then these weights, what do you think the gravity is on Jupiter? What do you guys think? Okay, because again, the mass is not changing. It's just the gravity that's pulling down on that mass is changing. So hopefully you said something around 20, right? So you got around 20, but it's really about 24. And if you look, it's because about 3 times, it's about 3 times as much, right? Not quite, but close. So that could have got you in the ballpark of 20, 21, 22, 23. So that's just showing you that, hey, basically all it is it's just a simple math problem. So it's mass times gravity is equal to the weight, and we'll show you that formula, okay? So cool. Some people ask this question is why the symbol of the pound is LB, because some people were asking about that. The symbol for pound is LB is because it comes from the Roman unit libra. The word libra is Latin for scale or balance. Some of you guys are like, that's a horoscope. Well, I'm just telling you, this is where it comes from, and that's why in the sign for Libra, it actually is a scale. That's because the word actually originally means scale. And that's why the symbol LB actually makes some sense for pound, because we are like trying to find the weight of things in U.S. customary units. Okay, so what is this used for? Hopefully you've seen this before. It's a scale, and you take a look. It will show you the weight in or the mass in grams, right? Or sometimes some of these scales will have pounds. But for the scale we're going to use, we are going to look at everything in grams, because we're not going to have such big things. We're going to have smaller things typically in a lab setting. If you were doing stuff in a larger warehouse or a larger lab, then you might go into kilograms. But typically in a classroom setting, you're going to be doing the things in grams. I will have these in the classroom tomorrow to show you guys, okay? Cool. So this is just called a digital scale, and we're typically going to measure things in grams or milligrams. It would be one of these two. Okay. And then you got these things right here. And what are these? Hopefully, you might know what it is. Maybe not. You already see newtons on there. So, oh, it's measuring weight. So that measures weights, right? But then it also, if you look here close, it also will measure what we would say grams. So that means it can measure weight, or it could measure mass. It could actually do both. So this is just called a spring scale. You don't have to write any of this down. It's just called a spring scale, and it can measure the mass or the weight of an object. Again, a spring scale can measure the mass or the weight of an object. This is typically how we're going to look at these. And if you're in class, we're going to take some time to kind of show you guys how to adjust them. So I'm going to show you guys one right now. Okay, so we're going to look at this one. This one goes up to what we would call 30 newtons, 30 newtons. And the way that you adjust it is at the top, and you want to get it to be zeroed. So I got to do some work to get it to 0. So I'm just going to turn the knob. I'm going to turn the knob here. I'm going to turn the knob and then see if we can get this thing adjusted. Ooh. Get it adjusted to 0. Okay. Cool. I think we turned the knob and now it looks like we are adjusted to 0. So any scale that you're going to want to use before you actually put any objects on there, you want to adjust it to 0. Also, spring scales are sensitive. So remember, it's based on the spring. So you can't be stretching it all the way out and doing all these things because then you'll mess up the spring. Then it won't be usable anymore. So again, make sure that you are adjusting it properly, and then also make sure that you are treating it gently. Okay, cool. So we will use these in the lab that we have upcoming, so I just wanted to introduce you to them and see how you actually would read them. And if you look here, you just want any scale you have, you want to adjust it to 0. Okay, cool. With that being said, I'm not going to talk anymore. You do have an assignment that will tell you about the metric system and how we got to the metric system and why America does not use the metric system. Okay, so it'll talk a little bit about that as well, like what happened in history to where America did not use the metric system. This assignment is due today, and that is everything for today's lesson. All right, y'all. Peace.